Now we're going to talk about the quantum mechanical harmonic oscillator model. I'd like to start by talking about some of the potential uses. So this is a model for oscillatory motion. It's also known as the particle on a spring. So it's the periodic motion of a particle on a spring. And of course, this is an approximate model, but it has a number of important uses, including it is used to describe vibrations in molecules, and in particular, when we're looking at vibrational spectroscopy, the quantum harmonic oscillator model is helpful in interpreting and understanding these results, and as well as making predictions, things like that. And vibrational spectroscopy includes infrared and Raman spectroscopy. It also shows up vibrations, molecular vibrations can also show up in the UV vis and in the fluorescence as sort of a series of lines kind of or bands superimposed on the main absorption. So there'll be what are called vibronic peaks, and so it's also in UV vis and fluorescence of sort of typical organic molecules, that sort of thing. And infrared spectroscopy gives you some structural information about the system related to, it doesn't give quantitative numbers necessarily for bond strengths or things like that, but it has the positions of the peaks are related to bond strength. And of course, the particular atoms that are involved have a certain mass, and that also shows up. And we'll see how vibrational frequency is related to the sort of spring strength and the mass of the particle that is, attached to the spring. So those are two primary contributions, factors or parameters that affect the vibrational frequency. And the harmonic oscillator model is extended, sort of is the basis, and extends into the phonon theory of solids, so vibrations of solids. And that's important for understanding things like the sort of acoustic phonons and the optical phonons. That's a concept that you may run across. And these phonons are important in determining the heat capacity and other properties as well, such as thermal conductivity and so on, of solids. And there are a couple of models. There's the Einstein model, which strictly speaking isn't really a phonon model. But it's closely related, and it describes heat capacity of solids in terms of the vibrations of the atoms within a sort of, each atom is in a sort of three-dimensional harmonic well, sort of like it's attached to three springs. There's another model that's more of the phonon model. The basis of the phonon model is the Debye model. It's a little bit more accurate, but also more complex than the Einstein model, which predates it. And the phonon theory, of course, is important as one of the basic theories in solid-state physics. And so if you want to understand the behavior of conductors, semiconductors, superconductivity, things like that, phonon theory is part of all that. And to understand phonon theory, you have to understand the harmonic oscillator. It's also the basis, it turns out, some of the mathematical features that come up in the harmonic oscillator model actually end up getting used and form the basis for quantum field theory, in that the electromagnetic field in quantum field theory is represented as sort of like a collection of harmonic oscillators. It's sort of mapped onto that. So that forms the basis of quantum field theory, which is typically more of a graduate level concept, but might be something that you occasionally run across some reference to, and so it's might be handy to know that involves harmonic oscillators. So one thing about the infrared and Raman spectroscopy, a lot of these are not, well, infrared in particular is not considered, it's kind of an older technique. It's kind of a 1950s type technique when it was most widely used. It's still sort of a workhorse. It's not the sort of go-to method for getting a precise structure of a molecule. That would be more NMR. However, it is a technique that's complementary to NMR, and there are certain cases where you don't need all of the information from an NMR, or where maybe you don't have enough sample, or there's some issue of, say, remote monitoring, and you can't sort of install a $1 million NMR setup, like on top of your smokestack or something like that. So things like infrared and Raman spectroscopy are going to be useful in those kinds of situations. So don't be too quick to dismiss infrared as being old. That would be a mistake. And again, Raman is it's a laser-based technique. It's maybe a little bit more modern in some ways, so yeah. So let's move on from that to. So I just kind of wanted to defend infrared there. It's not, of course, doesn't have the same position as nuclear magnetic resonance in the sort of collection of techniques that chemists and chemically related engineers and scientists would use, but it's still useful, still worth knowing. Okay, so now let's move on to the physical picture. We have some sort of wall or something, and we connect a spring to it. And then we have a mass. And the spring is described by a spring constant K. And we also want to set up coordinates. So we'll set x equals 0 at this sort of equilibrium position, and then this would be the plus s plus x axis. And so that's the basic physical picture. We have some sort of spring. It's connected to some fixed point, a wall or something. At the other end, we have a mass m, and we have some sort of way of measuring the displacement. Maybe we put a ruler at it, and then we set the 0 of the ruler at the equilibrium position. That's when you sort of leave the mass alone, and it's any vibrations have died down or whatever, and you've got just a mass without any external force on it in its equilibrium position. So that would give x equals 0. And then we want to introduce Hooke's law. Which is that a displaced object attached to a spring is subject to a returning force proportional to the displacement. So in terms of mass, it means that there's a returning force, we'll call it Fx, which is equal to minus Kx. So there's a returning force, so that's where the minus sign goes. So if you pull on the spring, pull on the mass, pull away from the wall along the positive x direction, there's going to be then a force, a restoring force, a return force, that's going to be pulling the mass. The force, of course, is supplied by the spring, and that spring would pull the mass back towards the wall. And so that would be along the minus x direction. And so we have this force along the x-axis is minus k times x, where k is some proportionality constant. We'll call it a spring constant. And it's worth perhaps taking a moment to consider what the units of the spring constant are. And if our force is in newtons, then and our displacement is in meters, then the units would be newtons per meter. And that's something to think about, and we'll be looking at what some actual force constants are for some particular molecules and so on, and the force constants are surprisingly in the sort of range of maybe 100 newtons per meter for a single molecule, which is sort of similar to what you might see for some actual physical large springs, or springs that you could grab onto. On some level, it's not surprising that the spring constants end up being the same because, or end up having roughly the same order of magnitude for like an actual physical spring versus the forces in a molecule, because of course the spring is made up of atoms, and so and the way things scale, they end up having roughly the same orders of magnitude. Okay, so that's force. Now we usually want to switch from force, and that's Hooke's law. Again, we don't know what the spring constant is yet. It's just a general constant. And this is a phenomenological law that was developed by Hooke. We don't really need to justify it. Actual springs seem to behave this way. Of course, at this point in the lecture, it's an open question of whether or not this is a good model for an actual molecule, but it seems like a reasonable guess, and that's usually how we proceed as scientists. We come in with a reasonable guess based on some analogy to some other system, and then we try to refine that guess. That's a typical strategy. Okay, so let's move from force to potential. You may recall, so the potential energy is given by, well, force and its relationship to potential energy is that force along the x-axis is minus dv dx. So flipping that around, our potential is going to be equal to minus the integral of f of x dx plus perhaps some constant of integration. And so then for this case, if we plug in force equals minus kx, the minus signs cancel, and we get integral of kx, which is going to be 1/2 kx squared plus some constant of integration. And in potential energy, we're often allowed to set our constants, set our zero of potential energy wherever we want. I mean, although we have to sort of keep track of it, we can't just sort of switch it around willy-nilly. But it's often customary to, when you get a constant of integration like this, to set it such that the constant of integration is 0. Another way to set the potential energy is to look at what would be the potential energy at the minimum and set that equal to 0. Now that's not always practical, such as in a Coulomb potential, the minimum is for an electrostatic potential, for a Coulomb potential, the minimum would be at minus infinity, so that wouldn't be a convenient 0. But in this case, yeah, setting c equals to 0 so is a reasonable minimum, and that just corresponds to the potential energy being 0 at x equals 0. So we can set that to 0, and that's our potential. And of course, we can keep track of that and see if later this choice of 0 causes us problems somehow. But for now, and of course, yeah, in an actual, say, in a chemical bond, this is not going to be necessarily, there might be other places where we want to set the potential energy 0. So that's like, for instance, we might want to set the 0 at the dissociated molecule, something like that. All right, so so basically our potential energy curve, it's a parabolic curve. Okay, and then before we go much further, of course, and actually we're not going to be looking at atoms attached to a wall necessarily. We're going to be more interested in molecules, isolated molecules. And while this gets to be rather complicated for 3 or more, or can be complicated for 3 or more atoms, we're going to at least look at the 2-atom case, and then the sort of diatomic molecule case, and then we can sort of assume that there are other methods for dealing with 3 or more atoms. So if instead of having a single particle attached to a wall, let's say we have 2 particles and they have a mass m1 and m2. And again, there's some spring constant. And there's some equilibrium distance between the two. We'll call that R0. And then we can define x equals R minus R0. So that would be the deviation from the equilibrium displacement of the two masses. And let's see, our approach to this, so you can imagine if this moves, basically there's going to be this kind of concerted motion where both masses are going to move at the same time. If there's a vibration, they're going to sort of move towards one another or move away from one another. It's kind of back and forth motion. And so in other words, each mass is going to move relative to some center of mass. And so for this kind of relative motion of a two-body problem, we switch to reduced mass type relative motion picture. So for relative motion, we can define a reduced mass, mu, such that 1 over mu is equal to 1 over m1 plus 1 over m2. Or we can say mu, we can rearrange and say mu is equal to m1, m2 over m1 plus m2. And so for our relative motion, that will be the mass, the sort of reduced mass of motion in this system. And I'm not going to really derive that. That's usually derived in first year physics, and there are derivations available online and so on. So what else? And then, yeah, let's look at some examples. So for instance, the reduced mass, by the way, these would be these masses are atomic, the masses of atoms. So we're going to have to go back and forth between atomic mass units and kilograms. A lot of times it's easy to initially calculate your mu using atomic mass units, since they're often since they're integers, and unless you're dealing with the relativistic corrections, but we can just use atomic mass units being the number of protons and the number of neutrons. And one atomic mass unit is the mass of a proton. And so if we had something like HCl, the hydrogen would be 1 atomic mass unit, mass of a proton. chlorine would be 35 or maybe 37, right? There are different isotopes. In fact, in an infrared spectrum, you're going to see different isotope peaks will appear. And so mu for HCl in atomic mass units is going to be 1 times 35 times 1 over 1 plus 35, 35/36. And we can say 35/36 times the mass of a proton, right? And so it's a little bit less than the mass of a proton, and this is typical. So the reduced mass for HCl is going to be similar to other diatomic acids, right? So it's going to be similar to HBr or HI. It's going to be a little bit different, but they're going to have a reduced mass that is, near 1. It's 1.05 or 0.95 or something like that. 0.9. Let's see, 35/36. Yeah, that's going to be about 0.97 or something times mass of a proton. And so it's good. You expect a number that's close to a mass of a proton. It's good to keep in mind because if you end up with something that's you're looking at HI or something, some other acid or HCl, and if you end up with a reduced mass that's 10 to the 5th times the mass of a proton, then something's off, right? You entered something wrong in your calculator. So it's good to keep in mind roughly what orders of magnitude you're expecting. And of course, a mass of a proton is 1.673 times 10 to the minus 27 kilograms. And so mu is going to be close to that. It's going to be 1.626 times 10 to the minus 27 kilograms, right? We expect it to be different in the third digit, and that's roughly what we see here. Okay, so I just wanted to talk a little bit about reduced mass, and then the other thing that we will. Okay, yeah. So then let's move on to. Yeah, we're not going to talk more about relative motion, sort of center of mass motion. Again, that's not something that we necessarily need to talk too much about. And in any case, if we want to move to triatomic and so on, then this reduced mass relative motion approach is modified for 3 or more bodies. Then you have a reduced mass, but you also have reduced mass that's associated with various what are called normal modes. And but we're not going to go into normal modes, but just we'll stick to diatomic examples, and but know that normal modes are out there. That it's covered in the textbook and later chapters on infrared spectroscopy, and it's a classical phenomenon that maps to the quantum mechanical harmonic oscillator as well. Okay, so let's also define something. Let's pull something from classical harmonic oscillator. So for a classical harmonic oscillator, its frequency and we're going to use the symbol nu. I think a lot of newer texts have switched to using F for frequency, but I'm still partial to the nu. Kind of looks like a windswept V with a pointy bottom. It is given by 1 over 2 pi k over mu to the 1/2, or the square root of the fraction or the ratio of k and mu. Angular frequency, so that's frequency in hertz. Angular frequency, which would have units more like radians per second. And what's given by omega is 2 pi nu. So it's going to have a slightly simpler expression. The 2 pi's cancel, and we get k over mu to the 1/2. Again, these are results from the classical harmonic oscillator. I'm not going to go into them, but we'll just use them as sort of collections of, we'll use them in a couple of ways. One is it's a way to sort of collect a couple of our constants together that are related to this system, one being the spring constant K and the other being the reduced mass mu. And we saw how to calculate mu. And we'll come back to some more examples. So if we say know the reduced mass of a system, we know the masses of the atoms involved, and we observe the frequency somehow, then we can determine the spring constant K, for instance. Or if we know K and mu, we can calculate the frequency that we expect for that given spring constant and reduced mass. And we can look at things like isotope effects. What happens if we change the mass of one of the isotopes and that changes mu, and how is that going to change the frequency? Another thing that we can do is, now that we have this relationship, we can also flip this around, and we can say wherever k shows up in expression, we can replace that with equals mu omega squared. And so like say our potential energy, we can use 1/2 kx squared, or we can use something like 1/2 mu omega squared x squared. Okay, so it's good to have some options here and have some extra equations that we can use that we might show up when we need to simplify things. Okay, so now we have all the pieces. We have our coordinate system. We have switched to a reduced mass, so we have an effective Hamiltonian, or we have effective equations of motion that involve a reduced mass and a relative coordinate x, and where x equals r minus r0. And then we know what our potential energy is. And so then our Schrodinger equation is, there's a kinetic energy term. So it's going to be minus our Hamiltonian which is the sum of kinetic energy terms and potential energy terms. The kinetic energy terms is, again, we've reduced this two-particle motion into the effective motion of the concerted motion, or the relative motion of the two-particle system about some relative coordinate x. And there's a reduced mass mu. So we're going to have minus h bar squared, and then instead of over 2m, it would be over 2 mu. And we have d squared dx squared. So that's the second derivative part. That's the kinetic energy part of the Hamiltonian. And then our potential energy part. And this is where, so far this looks similar to the particle in a box, except where we've replaced mass with reduced mass. But then we're also tacking on a potential. So particle in a box did not have a potential. So this is our first time that we actually have a Hamiltonian that has an actual potential in it. And this is 1/2 k x squared. And then what we have to solve is the Schrodinger equation, where h psi equals E psi. So we need to try to solve this differential equation. And there are various ways of trying to solve this. Okay, we can try various functions, or kind of use inspection, some intuition. In fact, we've run across a function already that is a partial, or that's a kind of a candidate solution to this problem. So that's one way we can do this. We can at least find one or two solutions by making some guesses about what the nature of psi is, or try some very simple functions, try exponentials, try sines and cosines, that sort of thing. And another way, and trial and error sounds like a infinite fishing expedition, but this is a fairly simple differential equation, and so we expect that there's probably a fairly simple function that would, or class of functions that would be solutions, and so it needn't take too terribly long to try several of these. And of course, you can look at the results for some functions to give you some hints about what kinds of functions you'll need. So that's kind of the inspection part. Sort of make an educated guess based on the nature of the equation. Another way to look at this is look at tables of differential equations. And they're usually written in some sort of simplified form, where here we've got, we're not going to find an equation that's going to have h bar in it, that's going to have mu in it. So you try to distill down your equation into the basic features, which is that there's a second derivative, with some constants maybe in front of it, and there's another term that has like x squared. And so we'd be looking for a function of the form y double prime plus, I don't know, a x squared plus or minus b y equals 0. Okay, so that's a fairly simple functional form. It's so you look for some kind of table of second order differential equations that have an x squared in them somewhere, in this kind of rough sort of form. And then we could do a change of variables, sort of switching, finding out what A is in terms of H bar and mu and so on, and in order to make to sort of match the two equations, and then we can then we have a solution to the differential equation, if indeed the table gives us a solution. And there's a third approach, which is called factoring. So it turns out that this you can factor into sort of a product of two first order differential equations, and those are a little bit easier to solve. So that is another approach, and we're not going to necessarily do that. I might come back to that later. But it turns out that factoring, when applied to this problem, leads to something that we call ladder operators. And they're very interesting and useful operators. They show up in other places too, as well as in angular momentum, and they can show up in quantum field theory. So ladder operators are another method of solving this. We probably won't have time to get into it, but we may circle back into that later in the course. Okay, so we're going to start by noticing that we actually had in one of the homework problem sets something that looked kind of like a solution to this problem. And so let's try that. And so we have this function, psi equals e to the minus a x squared. And so that's an exponential. E, of course, here is, you have to be careful. This is that's the 2.71 something or other number. It's the Euler's number. It's the base for the natural log. So this is an exponential function, e to the minus ax squared. And you've actually seen this curve before, perhaps. It's likely you've seen this before. And this is the sort of simple functional form that for the sort of bell curve type function. So this is this function is often called a Gaussian. And it has to do with it's Carl Gauss's probability distribution function that sort of helped start the modern era of statistics. And yeah, this Gaussian function, of course, it shows up in Gaussian blurs and Photoshop and things like that, various filters. But yeah, so this Gaussian function is going to be our trial function. And with that, I think I will end this lecture. And so next lecture, we will try taking second derivatives of this function and then try seeing if we can fix it up so that it's a proper solution to the Schrodinger equation for the harmonic oscillator. And then that's just one solution. We'll have to, it turns out we'll get a range of energy levels, a series of discrete energy levels, and we want to get a complete description of that. And then we'll move on to things like the other operators and their expectation values, and applying this to some specific vibrational spectroscopy problems.